forces acting on the system, the entire system. Basically, mass element is there, on which spring element, theoretical spring element, we know that it has zero mass, only it has a stiffness K. Mass element alone has a mass M, and which is supported by this one. So, and if I pull the mass element by applying a force F of T in upward direction, I say that the force is acting on the mass element. Okay. There are two forces acting downwards. One is called the spring force. Other one is called as gravitational force. Apart from that, another force is acting, which is called as inertial force. This is called as inertia or inertia force. Okay. Now, one force is acting upward. This is the force we have applied. That is input applied by us. But there are three forces acting downwards, which opposes the motion of the mass element. We know that already when we talked about it. So, for example, the spring has a length of, for example, 10 centimeter, and one end we have put a mass element. The mass element also has some height. We know that it is something like a cuboid. Even if you think that it has a cuboid, it has some height. And generally, when we talk about mass element, we talk what is called as COG. COG is center of gravity. We call COG. That point is taken as center point of mass element. Now, from the ground, this is reference on which spring is attached up to the COG point. For example, if it is 12 centimeter, this is height. This height I call it as X of T, current position of the mass element from ground reference to COG point. I call it a X of T. Now we are applying a force F of T. That means I am pulling the mass element upwards. Now the mass element will try to move from the current position to new position. In that case, what will happen is I can say that I have my mass element and the spring is stretched a little longer depending upon how much force we have applied, F of T. Now this is my COG point and this is my spring and this is my mass. I can say that from the reference point or tabletop where the spring is at one end is attached to COG point, because of I have applied a force. For example, I applied 10 Newton force. Now my position of the mass with reference to this is increased. Previously it was 12. Due to force, I say that it becomes 14 cm. That means delta X amount of the position is increased from the previous position when there was no force. When the force is applied, I said 10 Newton, the mass has moved to new position. I say that is 14 centimeter. That call like delta X. So this I call this as X2 of T, and the original position I call X1 of T. Okay. Now I wanted to find out the input-output relationship in terms of the mechanical system what we have. To understand that, we always draw what we call a free body diagram. That free body diagram is this, right? The mass element is there on which I am applying an external force input. I am pulling upwards, but there are three forces which are acting downwards. One is the gravitational force, other one is inertia force, third one is spring force. Okay, but now we need to model gravitational force is always acting on the spring. Okay, and that force we can ignore whether it is stationary or when it is moving up when you apply. So this force we can ignore. There are two forces which are actually opposes the upward movement of the mass element from the original position of 10 centimeter to new position, which is 14 centimeter. Now we know that the spring force. So that means there is a force exerted by the spring. That is what we call the spring force. Other one is the mass element has a mass. And because of that, there's a gravitation pull is there. Because of that, there's a inertia force is there. That force we called as inertia force. And there are two forces. And we know that the spring force Fs. Already we talked about Fs is nothing but K into into x of t. Nothing but the spring stiffness multiplied by the spring length. Okay. Next one is the inertial force. This force is due to the mass element. That we know that inertial force F of m is nothing but mass multiplied by d square by dt square of x of t. X of t is nothing but position of the mass element with the reference level. So this we can write it as m into a. We know this is nothing but acceleration. Now that we have two elements, using two elements, we formed a mechanical system. That mechanical system is shown here. Correct? Then we have written the free body. We have shown the free body diagram. From this, we can write the mathematical equation which represents the entire system. That is nothing but F of t, which is nothing but input force applied on the mass element. That means pulling upwards. Correct? We are tensile force is applied, so we are pulling upwards. That force equal minus the spring force. This is spring force. This is input force. This is the spring force. I say Ff. This is nothing but inertial force If equal to 0. Using the Newton's law, we can write this equation. This can be, again, we can write as, F of t equal to, okay, we retain F of t in left side. This entire term is moved to right side. So left side you have F of t equal to m into d square by dt square of x of t plus k into x of t. Now, this is called a time domain mathematical equation or mathematical time domain mathematical model. The equation which represents the entire system, including input. Now, this is converted into Laplace equation, Laplace transform. Using Laplace transform, you can convert this differential equation, second order differential equation. This is second order differential equation into an algebraic equation. If you convert to algebraic equation, the equation become very simple to do the calculations. So the algebraic equation Laplace transformed the model is nothing but F of s equal to m into s square into x of s, where the s square represents d square by dt square. The term d square by dt square, if you convert it to Laplace domain, it will become s square, where s is called a Laplace variable. It is called a Laplace variable. Okay. Now, then variable x of t become x of s plus k multiplied by x of s equal to, this can be written as, because you can see that in both the equation, x of s is common. I pull out the x of s outside. So f of s can be written as ms square plus k, x of s into multiply ms square k. So now I can write x of s from this equation. I can write f of, correct, x of s equal to f of s divided by ms square plus k, and this can be written as f of s multiplied by 1 by m equal to s square plus k by m. What I am doing, I am dividing this by m, this also by m, numerator denominator of the equation by m. In that case, I will get f of s divided by m, that is what written 1 by this one. Now I can write the final transfer function of the spring mass system, which is now g of s equal to X of s divided by f of s. We know that T of s is called a transfer function of the system. Transfer function of the system generally represented capital G equal to X of s is the output of the system. F of s is the input. X of s is output, this one. So if you write like from this equation, you can get that 1 divided by m equal to 1 s square plus km by this one. This is my transfer function of my spring mass system. So this is my spring mass system transfer function, which we derived from the basic equation of a spring and mass element. This is my system. This system equation, this is called time domain equation. From that, we got the Laplace domain equation. From that, we can find the final transfer function. Now, this transfer function, generally, when you see that this is equation, when I want to show graphically in control system book, it will be written like this. It will be shown something like this. A square box within the transfer function will be written G of s equal to 1 by m divided by s square plus k by m. This is what called as the block diagram representation of the spring mass mechanical system. What is the input? Input is f of s, output is x of s. So this is how we derive. This is for a spring mass damper system. Only 2 elements. Now let us see another example. Spring and damper system. In previous example, spring and mass. Now we are having 2 elements, one spring element, one damper element. We can build a mechanical system. If I want to show that this is nothing but generally we use in automobile, that is what you call a shock absorber. Shock absorber has 2 elements connected in parallel. So this is the damper or damping element. This is my spring element, and it has a stiffness Ks, and damper has what you call damping constant C. C is called as damping constant. Okay. Now, one end of the system, please see that there are 2 elements. One is spring element, other one is a damping element. Both are connected in parallel, and one side of that is connected to ground, or it is fixed, so it cannot move. This end cannot move. In another end, I can apply force, F of T, that is my input. The force can be compressive force or it can be tensile force. I can apply any force. It can be tensile force. F of T is input. Now, this is my mechanical system. If I wanted to write the mathematical model of this system, I can write, this is my mathematical model. What is my input? Input is F of T equal to the spring force, K into X of T. This is nothing but spring force, where Ks or K. Many books they put just K. For understanding purpose, sometimes I put even Ks. That is nothing but Ks is my spring stiffness. Okay. Then X of T is the, if I apply a force, what will happen? The damper also will move. If I apply, for example, compressive force, the damper also will move, and also spring also get compressed. The length of the spring get reduced. Length of spring is reduced from the original size. From its original size. Similarly, the damper, in damper we know that a piston moving inside the cylinder which is filled with viscous oil already. So the damper piston also moves. That means this also moves inside. Together, spring is getting compressed, the piston moves inside damper. So overall, since both are connected separately, from the original, they go to new position. I can say that, I can draw it like this. When I apply, initially F of T was 0. Now I am applying, for example, 10 Newton force. Then what happens? My spring will get compressed. My damper will also move something like this. Okay, the spring length is reduced. My damper originally had this much this position. Piston alone moves inside. So the total displacement I call it delta x of t. Right? Many times here we always say just x, but actually change in length only. So now this x represent from original position, it was here. Now it has moved to new position. This position. This was x1, I call it. This is I call x2. So the length, the position of the entire system change. That means piston has moved in by delta x. That is delta x is nothing but x1 minus x2. Piston also move together, they move. There's a displacement because of the force, there's a displacement delta x, which I can call it. So in this equation, we are saying that the f of t equal to ks into x of t, which is called as spring force, plus kd is called a damping constant. Already told you, some books write in c, some books they write a small b, in some book they write as kd. You can write anything. This is the convention used for representing, or notation used for representing damping constant damper. Now, the damping force generated by damper is proportional to damping constant multiplied by d by dt of x of t. This is x of t. X of t is nothing, change in displacement. So that is nothing but velocity, change in displacement rate at which displacement happening, we call it a velocity, we call v of t. So d by dt x of t is nothing but v of t. So right now we wanted to represent everything in the same notations. So we are not going to write v of t, we leave it d by dt of x of t itself as it is. And this represents what you call a damping force generated by damper, similar to spring force. So now, according to Newton's equation, we can say that the input force equal to the force generated by spring and damper. These two are opposing the movement. When I apply the compressive force, the piston is trying to move in the damper. The spring also getting compressed. That is opposed because the input force that they need to get compressed. That is opposed by the spring force and also the damping force. That's why we say input force equal to f of t equal to the opposing force, which is the spring force plus damping force. So this represents our spring and damper mechanical system. So you can take the equations. So we know that first when we write the equation, we write everything with respect to time. I told you this is x of t means with respect to time, the displacement is happening. Force is changing with respect to time. Everything in the universe generally happens with respect to time. At time t equal to something was not there, now it is there. Initially force was 0, now you are applying force. Initially the spring had some length. As you apply force, the length is reduced after some time. So that's what we are saying, we are changing. That's why this is called as time domain equation of spring and damper system. This is what we call as mathematical model of spring and damper system. I have only two elements. Now, from again you can see that it is a first order differential equation because you have a term d by dt of x of t plus k into this one. This is a first order differential equation. And solving differential equation, whether in computer or manually, complex compared to solving algebraic equation. So what I do, I apply Laplace transform to the equation. Laplace transform is applied to the equation, time domain equation, so that the differential equation will become a algebraic equation. That is the advantage of applying Laplace transform. If I apply Laplace transform, and I will tell you, you can see that the f of t it become f of s. This s represent Laplace variable. That means the equation in Laplace domain you can understand. So the t is replaced by this one equal to k. Any constant in the time domain equation will be represented as it is in Laplace domain. And the x of t, please note that generally in control engineering or the mathematical operators, if it is a variable, correct? In mathematics, we say variable, that means value is changing. It is always represented small letter. In control system, And most of the differential, when you write equation, all these things, we use small letter, small a, small b, small c, like that. So in fact, this should be written as f of t. Correctly, if you want to write, means you have to be referred to f of t. F of t is input force, f of t, that's why I written here. While typing, correct, it may be kept as by mistake f of s. So f of t equal to k, which is nothing but spring stiffness, multiplied by x of t. X of t is spring length. So spring length will vary when apply force. That's why it is written in small letter x, and within bracket t means the length of the spring will vary with respect to time when a force is applied, which is also varying with respect to time. Plus kd is called damping constant. As I told you, some books it put c, some book it is b. So I can just change this as kd. So kd multiplied by d by dt of x of t. So x is small letter. Now when I do the Laplace transform, what happens? The f of t become capital F, within bracket t will represent a small s, equal to k. The constant remains as it is. This is the spring stiffness. It remains as it is, multiplied by capital X of s. That means we know that it is converted to Laplace domain. And please note that in differential equation, which is in time domain equation, any algebraic term will not change as it is. There is a multiplication term that remains as it is, k into capital X of t. So that means multiply as it is. This addition will come as it is. And again, this is a constant that will be coming as it is, this one. And the only thing what happens is that the d by dt is a differential operator, we call in mathematics. The differential operator will be replaced by a Laplace variable with s power 1. Correct? S power 1. That is just s. And if I have second order differential operator, d square by dt square, in your mathematical model, we are going to see in the subsequent slide, that will be replaced by s square. If I have dq by dt cube, then that will be replaced by s cube. Like that, if I have d power n divided by d power n divided by dt power n, this will be replaced by s power n. Just remember this when you want to transform the time domain differential equation into Laplace domain. Okay. Now that we understood this one, and we will write the complete equation. What we have is, so the kd, this is a constant, damping constant that remained as it is. D by dt will be represented by s power 1, and the x of t is replaced by x of s. So this is called as Laplace transformed equation or model, Laplace transformed mathematical model. I told you mathematical model is nothing but writing individual system elements, their input-output characteristics, and connecting them to appropriate mathematical operators, you get the system equation. Again, I want to show that already we have written the system equation in time domain. Let me remove all these things so that it will be clear to you. You can see it. F of t is nothing but k into x of t, which is the spring force, plus the kd into d by dt x of t, which is the damping force. These two represent system element which produces opposing force to the force applied as an input. We are converted to Laplace. Once we apply, now we can write in similar case, previous case, we can write the transfer function g of s equal to x of s divided by f of s, where the x of s is called as output of the spring and damper system. That is nothing but position of the piston or the spring length, change in spring length, divided by input force f of s equal to 1 divided by k divided by kd divided by k plus multiply is s plus 1. And this can be written as 1 divided by k divided by t into s plus 1, where the t represent, the capital T represent this term. This term is kd by k is called as, you know what is kd? It's a damping constant damper. K is nothing but spring stiffness. We can put subscript also to understand clearly. So the damping constant divided by the spring stiffness of the spring damper system represent what you call a time constant of the system. So now this is my transfer function of the spring and damping element. Okay. Now in the exam, sometimes you will be asked to find out the you will be given with what is the KD value, XXX and KS equal to YYY, correct? And when I give F of t equal to ZZZ, some value, now you will be asked to write the mathematical model of this system in time domain equation. And you convert into Laplace domain, find the transfer function. These values will be given. You'll be asked to find the transfer function, which is nothing but X of s divided by which is G of s. Find out. Then also find the time constant of this first. This is a first order system or the spring damper system. Calculate this, because already you are given KD is given, KS is given, and F of t is given. Then you can write the mathematical model in time domain, convert to Laplace domain, find the transfer function. Once you find the transfer function, then this also you are going to substitute. KS is available, you know, KD is available, KS is available. You can do that. If you substitute, you will get some value. For example, if I say KS equal to 5 and KD equal to 10 and F of t equal to say 20, I can substitute all those things. Finally, you will get one value, 1 divided by KS, and KD already know, KD equal to 10, KS equal to 5. That means 10 divided by 5, this will become 2. Then you will get, what you will get is 1 divided by KS. KS already told you 5 divided by TS equal to 10 divided by 5 multiplied by S. This is the first term, this term plus 1. So you can say that this is 0.2 divided by 2s plus 1. This is my transfer function. Okay. Even F of t is not given, you can get the transfer function. Okay. Transfer function, you will get it. Okay. Then we know that once you have the transfer function, what you can do? We know that transfer function G of s equal to X of s divided by F of s. Now, transfer function already I have. What I have? My transfer function for this system is given as 0.2 divided by 2s plus 1. This is my transfer function, for which I am giving input F of s. And I wanted to find out the... now, if I say F of s equal to 5 Newton force, then what is my X of s? X of s equal to the input multiplied by the transfer function. Already I told you, the transfer function also called as gain of the system. No doubt. It is also called gain of the system. Okay. Now, that means multiplied by 0.2 divided by 2s plus 1. This is what my going to my output. Okay. So now the output, then what we have? My X of s output equal to, if I see that, I can write that is nothing but 5. This was 1 divided by 5 into 0.2 equal to 1 divided by 2 plus 1. This is my system output. When I give my input F of s equal to 5 Newton force, my displacement will be this. This is still in Laplace domain. You can convert into time domain and you will get X of t, you will get small x of t, you will get when you take what you call an inverse Laplace transform. Inverse Laplace transform. If you do inverse Laplace transform, you will get the output of the spring and damper system when you apply input force of 5 Newton. Now, we understand that just by developing mathematical model, what is the advantage? You are not going to construct it, take a spring. Actually, when you wanted to develop the system, physically you have to, before the computers are available, which can do all the calculations, this one, we need to make a spring and find out what is its spring stiffness. And similarly, you have to make a damper. Then you connect the spring and damper and make the shock absorber and apply the force in the workshop and apply 1 Newton, 2 Newton, 3 Newton, correct? You will apply F of T and you will find out what is X of T. 0, 0 displacement. Apply 1, 2, 3 like this. You will get something displacement like this. This is how then you plot this, you will get a curve. From that you find the equation, correct? Now, that means physically you have to spend a lot of money and effort. Now, in mechatronics way, that means mechatronic way is nothing but new. First, develop the mathematical model, this model, and find out the transfer function. Once transfer function is available, by substituting these values in the program, you write program with C or Python, correct? I can write with Python or MATLAB program, any language, or Fortran, any language. Then supply this value to the equation, and you can find out what is the displacement. That means without making the physical system, spring and damper, using this mathematical model and transfer function, you can write programs and tune your system. What is tuning system? If I want my X of S to be, correct, when I apply F of T equal to 5 Newton, the length change should be only 2 centimeter. Now, what you are getting X of T for this is, for example, 3 centimeter. That means this is not acceptable to you. What you have to do? If you want to bring it down, in this equation, see the transfer function. In the transfer function, you have KD, KS. These are the two parameters you can change. By changing, you can change the gain of the system. Gain of the system is nothing but transfer function. So, if the gain of system is changed, then for the same input force, you will get 2 centimeter. Till you get 2 centimeter, you vary value of KD and KS in this equation. That is called as tuning the system. Note down. It is called as tuning the system to get the required output. So this you can do by running program itself without making actual physical components. Otherwise, what you have to do? First, you made one stiffness KS equal to 10, damper equal to 20. You made the damper also took the wire, correct? Spring steel wire, and made a coil, and you found what is this stiffness, and you made a damper, and you found the value. You both are connected as parallelly. Then you got the shock absorber, which is nothing but spring and damper. You applied force, and you saw that the displacement when you apply 5 Newton, it is 3 centimeter. Then what you do? Olden days means again you discard the spring or this one of this and get a new spring with, for example, K is equal to 8, correct? And keep this equal to 20. And you can again apply force and find out. This is how you're doing. That's called physical modeling, which is you are going to waste spring material, damper, fabrication, all these things. Now, with this advanced computers, and software programs, algorithms, and compilers available, you can write the programs, MATLAB, all those things, and apply vary the constant, KD, KS, all those things, and see for given code whether the X of T is coming as you get. If it is okay, then you stop. That is called as iteration. You do. That's what I talked when we talked about mechatronic way of this with the flow chart I explained to you. So now we saw the second system, how it works. Okay. Second system, we saw that is spring and damper. Now we'll go to the next third system, little more complex. We saw single element, spring element model, damper element model, and this one. Then we connected 2 element system, correct? Yeah, spring with damper and spring with mass element. Now we see a third system, which we call as spring mass damper system. So spring mass damper system, when I wanted to see, what will happen is it will have a spring element. Okay, it will have a spring element. And it has a mass element. And it is connected to a damper. This is KD, damping constant. This is mass. This is called spring mass damper system, in which I can apply a force F of T input. When I apply input force, the spring will get compressed, and the damper also, the piston will move inside. The length between the damper and these two ends will reduce. Okay. So then mass will move along with it. Now my interest is, for example, with respect to ground plane, this is my ground plane. I wanted to find out current position. My current position COG. This is COG of the mass element. This distance I say x of t. This x of t is my output. Output my system. When I apply a force which is input. Okay. When f of t equal to 0, this x of t equal to, for example, x of t equal to 20 centimeter. Current position with respect to ground reference plane. Now I apply, this is for f of t equal to 0 without input force. Now I apply f of t equal to say 5 Newton force. That means the damper will reduce its size. Spring also will get this one. I can draw it for understanding purpose. So I can say that spring becomes smaller. The mass element will not get compressed because it is fixed. The size you cannot compress here. That means my damper has become something like this. So I say, okay, for example, so this is my delta x. Originally, this was x1 of t. Now, new position, x2 of t is this, nothing but because of the force applied. Now, I applied f of t equal to 5 Newton. Because of that, my spring is get compressed, length has changed, it's become smaller. The damper piston also moved inside, so it got a new position, my mass element. So this is moved to a new position. So now I want to write the mathematical model of this spring mass damper system, which has 3 elements. Okay, so we know that this is f of t. F of t equal to input force. What you are supplying, it should be equal to mass into d square by dt square of x of t, which is nothing but m into a. This can be written as ma. Already we know that. But we wanted to keep a uniform as a displacement as a common unit. So that's why we are not writing the acceleration at all. We are writing only the displacement. So acceleration can be represented by d square by dt of displacement. That's what I have written here. Okay. Plus kd is called damping constant multiplied by d by dt of x. This is nothing but velocity v of t. This is acceleration, this is velocity. This is x of t. So plus k, we can say ks into x of t. This is nothing but spring force. This is called damping force. I say df. Then this is called as inertia force. Inertia force. I think previously we wrote fm. This we called as fd. And this is called as fs. Spring force. Now I can say that that's what I written here. Please see here. The net force is nothing but input force, correct? Equal to f of I plus, that is for inertial force. Sometimes we write a fi also. Okay, fi plus fd plus fs. Inertial force of mass element, damping force of damper, spring force of the spring should be equal to the input for net force. Now already we know that from this we can write the mathematical model. That's what we have written here. Note down this one. Now this is in time domain equation. What is this is a differential equation. Time domain equation differential. What is the order? This is d square by dt square. So it is a second order differential equation. Previous was first order equation. I told you solving first order equation little complex compared to solving a different algebraic equation. What algebraic equation means, it will have only 4 mathematical operators: addition, subtraction, multiplication, division. So this has a differential operator. First order differential operator, there's a second order differential operator. Solving a second order differential is much complex than first order equation. So if it is third order, still going to be complex. That is why time domain equation, once you write this system model or mathematical model of spring master damper system in time domain, I convert into Laplace domain. Laplace again very simple. The f will become capital F, force will become, the t will become f of s. This represents input force. The mass is a constant, so it will become m only. D square by dt square will become s square, as I told you in the previous slide. X of t will become capital X of s. I think small mistake. I can write. I'll write like this. F of s equal to m into s square into x of s. This is how you have to write. Plus kd into s into, because d by dt s multiplied by x of s plus k is the stiffness ks. I can say ks multiplied by this is x of t. This will become capital X of t. Please note that in time domain, variables are represented small letter. In Laplace domain, it will be made as a big letter. Same variable. Small x will become capital X, and similarly, small f will become, force is a variable, x of t displacement will both will become capital, and the constant will come as a differential operator will become s square or s depending on. So this is my Laplace domain mathematical model of my spring mass damper system. Now that we have this, we need to find what is it called as transfer function. Okay. Now if you want to transfer function, g of s equal to, this is capital X of s, output divided by input is nothing but 1 by k. 1 by k. I think you have noted down this Laplace equation. Okay. Now we'll write the transfer function. Transfer function g of s equal to output x of s divided by f of s is nothing but 1 by k in the numerator divided by s square plus m by k plus s into kd divided by k plus 1. Again, I told you, you can write ks, spring stiffness. Mass divided by spring stiffness multiplied by s square is the denominator first term. Second term is s into kd, that is damping current divided by stiffness plus 1. In numerator, 1 divided by this one. So now this equation can be finally written as g of s equal to, numerator remains as it is 1 divided by ks divided by this m by ks can be written as t square. This term is written as t square into s square, because s is here only, the small s. Then the second term kd divided by ks can be written as kd divided by ks. This term can be written as 2 delta t, capital T. So this term is written as this 2 delta t. Then the remain as it is. Now that we have complete transfer function, in which what is t? T is called a time constant of the system. T is called as time constant. Note down. We called as time constant of the system is t equal to root of m by k, and the delta is called as damping ratio. Note down. Delta is called as damping ratio. In some books, it will be represented as eta. Correct? It can be represented as a eta. Greek letter eta. Some book they put a delta, which is nothing but kd divided by cc. The cc here is called as critical damping constant. Kd is a damping constant, a damper. Already we know that. That is the fundamental property of damper. That divided by cc is called a delta, where cc is called as critical damping constant. That can be computed using this formula. Critical damping constant cc equal to root of 4 into m into ks, where m is the mass element value, k is the stiffness. If you know that, you can multiply by 4, then if you take a root, you will get the cc. That cc will be substituted here. kd is a damping constant. Please note that students get confused two terms. One is called damping constant of the damper. That is generally written as C or small b or kd. Any one of the notation be used. That depends upon, already we talked the damper. In previous class we talked, for example, linear damper, a piston moving inside with the orifice in the edges side of this one. And already we got the equation how to compute the damper, how much force it creates, all this in previous class. So I'm not going to repeat that. So that is called damping constant of the damper, which is a fundamental characteristic of this one. The damping ratio, if you see that, the damping ratio consists of all three parameters, correct? Delta T equal to KD divided by CC is nothing but root of 4 MKS. This is what the damping ratio. Damping ratio of the second order system. We are talking about damping. the damping ratio not only depend on damping constant, it also depend upon mass of the mass element and spring stiffness. This is a total equation. This damping ratio going to decide how the system output will happen when a particular input is given. What is the input? My F of t, force is given as an input. Then displacement, X of t, what is the displacement? Displacement mass element as spring mass damper element. Position of the mass element from the current position to new position and apply a force. That is called as output. This is my output. This is my input. If I change my input 0 to 100 Newton, for example, and my displacement may 0 to say 10 centimeter or 20 centimeter, how that is controlled by this gain. Correct? The gain of the system is nothing but transfer function. So the gain is decided by spring stiffness, mass, how much, what a mass element value, how many kgs mass, and also the damping constant. So the transfer function, you can see that it depends on system parameters. Correct? So for you given system parameters, you get a transfer function, which is also called the gain of the system. We say that gain. I buy something, sell it for something, for somebody else, some other value. But that's what we call a gain. Similarly here, if I give an input, this is my spring mass damper system, a transfer function is written here. If I give input F of t as a force, how much the X of t, the position of the mass element will move with respect to the current position. That is what output. So that depends upon the gas. We know that X of t equal to F of t multiplied by G of S. Correct? G of S. So that means the gain is going to decide. Gain depends upon the system. That means what is spring stiffness, what is the mass of mass element mass, and also the damping constant. If I vary this value, my gain transfer function will vary. Then for a given input, you get particular output. That's what we are interested. So now, before closing, I want to close today's class. Before that, you note down this equation. So if you are in the exam, if you are asked to draw the function, the spring mass damper system, you need to draw the spring with mass with a damper. And here we are applying F of t. Other end is grounded. This is my mass. This is my stiffness. This is my damping constant Kd. Now, from this, you will be asked to derive the transfer function. You need to derive the transfer function. So that means you have to write the thermodynamic equation, write the Laplace transform of that, then write the transfer function, and finally up to this. If you write this, now if I may give value of Kd and I will give Ks and also the mass. All these values are given in your problem. You can write the final transfer function substituting value. Again, it will be a numerator divided by denominator polynomial. Then you'll be asked to find out what is time constant of the system. That means you can compute using this equation. Then you'll be asked to find out the damping ratio of the second order system. You can find out by substituting Kd and finding the Cc. That is critical that you can compute to this. One that is known, you can substitute that, you can get it. Final value, because this is the equation we have given here. Okay. With this, I will stop today's class.
Recording stopped.
If you have any question, you can ask now. You can unmute now and ask questions.
Sir, in the first case where we spoke only about this spring and mass, the force was acting away from the mass.
Spring mass system, this one?
Yeah. So here the force was acting away from the mass, but in the last case where we have spring mass and damper system,
you can apply anyway. You can apply anyway,
okay.
No issue. Correct? It can be compressive or tensile force, but the mathematical model is going to remain as it is. Only thing, value is going to change.
Okay.
See, the displacement is maybe like this. original length, for example, I showed you 12 centimeter, correct? This is 2 centimeter from here. This is 10 centimeter, 2 centimeter, 12 centimeter. If you apply a tensile force F of T like this will become 14 centimeter, correct?
Yeah.
For example, you apply 5 Newton force. Instead of that, if you apply compressive force, same 5 Newton, this length will become 10 centimeter, correct? The spring will be compressed by this one. This will be expanded, compressed. That's what is going to happen.
Okay. And here this is like a suspended system where it is the immovable part is down, but in the last system where we did a spring mass damper, it's not really suspended, isn't it? So there we have.
Yeah.
Because how does, because you in the beginning you said there are 3 types of forces which act. One is spring inertia and then gravitational force. So if the position changes, then the gravitational force will come into play, isn't it?
Yes, it will come into play, but that's what I'm saying. For example, if everything is put on a table, correct? You have a spring, correct? Your mass is there, and there's a damper. All those things, because for example, the mass element has some wheel, something like this, correct? Horizontally. That means it is supported, and when we are applying force horizontally, correct? So the mass is remained as it is because already is supported. Now, mass is not going to act on it. That is gravitation force, no effect, because already is supported on the table top, and the mass is put on your wheels. So if you apply a force, it can move this way only. Force is going to act only left or right, compressive or tensile force.
Okay.
In that case, as you told, the gravitation. But if they suspend in the air, the entire system, then the gravitation will pull down.
Yeah. Yeah. Okay, got it. Thank you, sir.
Okay.
Thank you, sir.
Okay, we'll see you tomorrow. No class. I think we don't have class tomorrow. Being a Gandhi Jayanti, I think you are holiday for you, correct?
Yes, sir. Yes, sir. Yes, sir.
So
Monday we'll meet, sir.
Monday we'll meet, but I want to have 2 extra classes before the midsum exam. Additional class. We missed it, sir, because 2 days the system was not working. Yesterday power went off, all those things. We lost a lot of time.
Sir, we can have it next week, sir. This week we are going to study the thermal
Exam.
machines.
Yes, very good, fantastic. So next week we'll have 2 additional classes. Okay.
Sure, sir.
Thank you.
Regarding that one idea, actually,
tell me, Amit.
Probably we might have holidays for the festival. So,
which festival?
Dashara, I guess in our company there is a holiday on 11th. Not sure about others. So probably Friday and Thursday we can have. I mean, that is just my idea.
That's what he said. No, next week you have exam 6th. After your exam, correct? Monday, Tuesday.
Amit, we will jointly discuss and we will tell to professor. It's not a problem.
Okay.
Yeah, that's what.
Okay. See you.
Thank you, sir.
Enjoy your tomorrow holiday. We'll see you on Monday. Good luck.
Okay, sir. Thank you.
Thank you, sir.
Okay. Bye.